All right, let's go ahead and begin. So the first half of class, we'll review what we did yesterday, and we'll learn a little bit of new material. And then the second half, we'll review 5 and 6. All right, what is an alkene? A double bond. What is the hybridization of a alkene? sp2. Trigonal planar, here's what we say. We also looked at elements of unsaturation. So if we have maybe this, what would we do here? Do you remember the formula? 2 times the number of carbons plus 2 hydrogens all divided by 2. Okay, so I'm going to plug this in. I have 2 times what? 6 plus 2 minus what? 5. Any halogens? Nitrogen? 1, so minus 1. All divided by 2. So 2 times 6 is what? 12 plus 2, 14. 5 minus 1. What? 4. 14 minus 4. 10 divided by 2. 5. So all you can tell me at this point is that there's a lot of either rings or multiple bonds. What is a degree of unsaturation? 2 hydrogens. It's the loss of 2 hydrogens. So if we have a single bond, or not single, a double bond, how many does that take? How many degrees of unsaturation? 1. A ring? 1. And a triple bond? 2. We also looked at some naming. All right, let's name both of these. What is the longest chain in the first one? What is it? Pentene. And where is the double bond? 2. Because that's the closest end. You see 1, 2 versus 1, 2, 3. And what is this? Chloro and carbon 2. Now, can you say cis, trans, or EZ on this? Yes. Because it's showing you the direction of the bonds. So let me show you. I'm going to half this. You see carbon to carbon. So half it right there. So which would be priority number 1, chlorine or methyl? Chlorine. Then over here, what's missing? Hydrogen. So then ethyl or hydrogen? Ethyl. So what is that? Or not cis, but Z. Okay, what about this one? So anytime it shows you, the direction of the bonds, you can put either cis, trans, E, or Z. So let's look at the next one. How many carbons here? 8, which is a octene. Where's the double bond? 2. And can I say cis, trans, E, or Z? Yes, you can. So let's look at it. Okay, do you agree that this here on this side of double bond, that's going up? And then if you go to the other side of the double bond, that directly is going up, right? So how are they both pointing? Up. And then how many are we comparing? 2, so we'll say it's cis. So let me show you like a trans. Actually, you could technically name it either way. You can't always say cis, but you can always use Z. Does that make sense? Because cis will occur if you have 2, okay? But you could also say Z. But if I have 3, like right over here, do you see I could not say cis, right? Because we're comparing 3. So I had to use Z. So you can always use Z, but you can't always use cis. So cis, and I'll put or Z right there. So if I had, let's say this one, let's name that one. How many carbons in the chain there? How many? 7? Where's the double bond? 3. 1, 2, 3. What is this? 3-methyl. Okay, so let's compare it. Do you see carbon, carbon, split right there? Now on this side, what am I missing over here that's not shown? Hydrogen. So between those two there, the top one. Now between this one and this group here, the bottom, because it's a longer chain. Your longer chain will always be a higher priority there. So I have, let's see what direction they're pointing. This one's pointing like up, and this one's pointing down. So that would be E. Anytime they're drawn in skeletal, you can technically say cis, trans, E, or Z. Okay, and that's pretty much what we went over yesterday. Okay, do you remember when we were doing like the E1 and E2 products, predicting those? Where do we put the double bond? The neighboring group, but how do we know which one? The longest chain, right? The reason you chose the longest chain because that would end up having the most branches off the double bond. And what they found is that's the most stable. So if we look at here, looking off this double bond, this carbon here, how many carbons are bonded there on this side? Off that carbon. 0, right? It's just a CH2. Is there any carbons coming off that carbon? No. So let's look off this carbon here. How many carbons, like directly bonded? Not counting the other double bond. Going this way. 1. So there's 1 branch, okay? Now let's look at this one. Now knowing how to do it, how many carbons coming off this one? 1 right here, that's CH3. Now what about this one? 2, okay? So that has 1 branch. This has 3 branches, okay? So the more branches coming off the double bond, like that, the more stable. And they have here the heats of hydrogenation. You see negative 127 and negative 113. The lower the number, the more stable. Basically, you see it's releasing that much energy. So do you think, hopefully this makes sense, a higher energy, or the less stable, the more energy kind of compacted in that molecule, okay? Think high energy, unstable. Now these are more stable, so a lower energy. So you see here, this one has a higher energy, so it's less stable, negative 127. Lower energy, so more stable. Now there's a trend here. Here, okay, R, remember, stands for carbon. So you see here, this double bond has how many red R's coming off of it? 1. This one has, or these 3 have 2. This one has, and that one has 4. So the more, do you see, has lower energy, higher energy up here, lower energy down here. Okay? And this has to do with stability. All right? So the more stable is the more substituted double bond. So what we've been doing, that Zaitsev rule, where we had, you wanted to make the bond at the longer chain, you were doing it without realizing it. So you're always making the more stable one. This is the reason why, or this is their rationalization, we should say. Okay, so let's look at, or right here, look at this carbon here. Is that sp3, sp2, sp3, right? And because it's all single bonds. Do you know the angle for sp3? Well, it has it right here. 109.5. Now look at this carbon right here. This is the same carbon. Do you see this carbon has 2 methyls coming off of it? And this carbon has the 2 methyls coming off of it? So same carbon, okay? But now it's a double bond. Okay, so that's sp2, and do you see the angle is 120? So which one is a larger angle? The 120. So what it does here, now the methyls, since they're coming off a double bond, are separated by 120 degrees. And over here, when they're coming off a single bond, the methyls are only separated by 109.5. So being separated by 120 is a little bit more favorable because they have the electron densities around them, so they want to be further apart. So basically, the more carbons that we can separate by 120 degrees, the better. Okay? So do you see here, how many branches coming off this double bond? Just the 1 right here. And then what about over here? 3. 1, 2, 3. Okay, so when it had 3 branches, it's more stable because all of these single bonds are now separated by 120 degrees. Anyway, so long story short, the more branches off the double bond, the more stable that double bond. Alkenes have very similar physical properties to alkanes because all we're doing is adding a double bond in there. So what intermolecular forces do we have? So we're looking at a carbon group with a double bond. Is there hydrogen bonding? No. Is there a polar atom in there, electronegative? No. So what's the only intermolecular force? Dispersion. Okay, so the same sort of rules apply. You see the branched alkenes have lower boiling points, and also so you want less branching and larger molecules, just like the regular trend we knew for intermolecular forces. Okay, so it's the same exact trends. Less branching, longer or larger mass. Okay, so synthesis overview. So we've learned how to make these double bonds basically through E1 and E2. Or elimination always makes a double bond. So now we're going to look a little bit more in depth into E1 and E2. So here, E2, we're going to look at dehydrohalogenation. D meaning it's getting rid of, okay? Hydro means hydrogen. And halogenation means also a halogen. So I'm getting rid of a hydrogen and a halogen. And then E1 also has a dehydrohalogenation. And there's also a dehalogenation of vicinal dibromides. So dehalogenation, what am I getting rid of? Halogen. And how many? 2. So we're going to get rid of 2 bromines. And then dehydration of alcohols. When you think of dehydration, what molecule comes to mind? Water. So we're going to be losing water. Okay, here's the basic mechanism for E2. I'm just going to put B for base. Okay, so what does a base like to take off? Hydrogen. So it's going to grab that hydrogen. Okay, and where does hydrogen leave its electrons? As a double bond. And then what leaves because of that? Bromine. Bromine's going to leave. So if you want, we end up getting HB and Br minus if you want to see the byproducts, forming this double bond. Now, do you see that this was the dehydrohalogenation? Because what 2 things did we get rid of? Base took what? Hydrogen, and then what left? Bromine, a halogen. So this is the hydrogen halogenation. Halogen. So we got rid of a hydrogen and a halogen. So this is the one we've seen before from chapter 6. Now there's additional information to know. Okay, if you use a bulky base. So remember we had a large bulky base sometimes? Here's some examples of these. Do you see that these are all really large compared to just putting like OH minus, right? Do you see that these look a lot larger than that? Okay, so these are examples of your bulky, large bases. Well, what I actually told you the other day wasn't completely true, of course, about having a large base. Now, it'll occur, but it actually changes your product a bit. Okay, so let's look at here. Let's see what's going on. Do you see on this one, this is considered a small base, mainly because I don't have like 3 branches. Do you see down here, you see that parentheses 3? That means that one's bulky. Anytime you see that parentheses 3, that means bulky base. If there's not a parentheses 3, then it's considered a small base. Okay, so this one's small. Okay, what's my leaving group on here? Bromine. Okay, so here's where the bromine's leaving. Now, where will I take a hydrogen off of? So you have, what's over here? Methyl? What's over here? Also a methyl? It's showing the hydrogen down here, but it's a methyl. And then how many carbons over here? 2, which is an ethyl. So I can either go towards a methyl, or an ethyl. What would I choose? Ethyl. So it would go, do we agree, right in between those 2 right there? So do you see that's where it went? It went right in between those 2 there. That's the Zaitsev product. See, coming up here, let's make sure we all see it. Do you see off this carbon, how many methyls do I have? 2. And do you see the 2 methyls? And then over here, this carbon, how many methyls? 1. And that's the 1 methyl there. Okay, now let's look at, and that's the main product. You see 71%. Now let's look at this one. It's the same exact starting material, except now they're putting in a bulky base. Now we would have predicted the same product, right? Okay, but only 28% of it is made. And look what is made. Basically the product we didn't predict, which is 72%. So let's look, let me draw this. Let's see. 1, 2. Okay, this is what we have here. And we predicted the most stable product would be taking that bromine off and putting that double bond right there. Because you see we have methyl, methyl, ethyl, right? So putting the double bond in between those two carbons, like that. But what they find with the bulky base, that one doesn't form. This forms. So let's look at this. Here is my leaving group, and that's not going to change. Now, where did I actually make the double bond? To what? Here to the methyl going up right there. Okay? So in between these two. All right? And so that went to the one of the smaller chains, right? Now, when it's the reason this happens, and this would be like the least stable product, is what you would predict, okay? This one's called the Zaitsev. This one's called Hoffman. This one is the most stable. That one is the least stable. Okay, what happens, the reason it happens is because our base is so bulky. It's really large. Now, do we like crowding? No. Okay? So it's already going to be more crowded than normal. So I have over here, I have that the bulky base can come towards an ethyl or one of the methyls. Which one's smaller? Methyl. And so that's why it ends up coming to the methyl. It's smaller, so it's not going to be quite as crowded when it takes the hydrogen off. So you end up forming the least stable only because it's faster to take it off that way. So, anytime, here's a summarize for that one. For E2, if I have a small base, which product do I form? Zaitsev? Yeah. Which is what? The least or most stable? But if I actually use a large / bulky base, which one do I form? Hoffman, which is what? The least stable. And that's pretty much will always occur. Now this is actually really nice. I know information-wise it's not, because it's another thing to think of. But if we come over here, and let's say this product right here, this Hoffman product, can cure everyone of cancer, every cancer possible, okay? And you just have to take it one time, all right? And you have to think, how can I make this? I need to actually make the least stable Hoffman product, okay? And so you have to think, oh, okay, I need to put in a what base? A smaller bulky base. If I put in a bulky base, I'm going to make, you know, this unstable product. Now, the bulkier the base, the even more likely you're going to make it. So if I put one of the really giant ones, you know, maybe something like this or this in there, this might go up to like 92%. Okay, so the larger you make your base, the more it's going to favor the Hoffman. Okay? Anyway, so that's why you have it. I know it's just more information to remember, but it is very useful because it might be what you actually need to make. Okay? So it just depends. Do you need to make the Zeit stuff, which is the most stable? And I would say most of the time that's what you're trying to make. But if you do need to make actually the least stable double bond, that's where you have to put in your bulky base. Does that make sense? When to use each one? Okay. Stereochemistry. Okay, so it's easier to do it this way than how they show it. Oh, wait, no, I don't want. Okay, so let's look at these two here. Put in our base. These are going to undergo E2. Okay, now the one thing with E2 is that once you're leaving group and that hydrogen 180 degrees apart. So looking at the first one I have drawn, are they 180 degrees apart? Yeah, they're kind of, trans-like. They're not actually trans because they're single bonds. We call them anti, actually. Okay, so this is anti. So whenever this reaction goes, what leaves? What are the two things that leave? Hydrogen and bromine. And then what do I form? The double bond. So when I do this, everything is in the right configuration. I don't need to change anything. What double bond do I end up with? Is that a cis or a trans? Trans. Now let's look at this one. My hydrogen and my bromine, are they 180 degrees apart? No, they're not. So I need to rotate one of them, right? Because when we're single bonds, we can rotate. That's how we did the Newman projections, right? Okay, so let's say we rotate this side right here. It doesn't actually matter which side you rotate, but just one of them. So what direction do I want my bromine to be? Down, which will force the methyl to go up. Right? Now are they 180 degrees apart? So what am I going to get rid of? Bromine, hydrogen, double bond right there. You see do you see that those carbon groups are exactly how they are shown, right? Up, across, down, up, across, down. And what did I end up with? Trans. Now let's look at see. Something like that. Okay. Are these 180 degrees apart? Yes. Okay, so do I need to flip anything? No. How are these two carbon groups pointing? Back or down, however you want to look at it. So when I draw them, and you can put them on a dash if you still want to. What do I have here? Cis, right? So you don't always necessarily make the trans. So all you need to do for the stereochemistry is analyze. Just look at your hydrogen and your bromine. Okay? Are they 180 degrees apart? If the answer is yes, then it's fine. Draw your double bond just like you would. If it's no, you have to flip one of the sides. Okay? So I'll think of one more and see if you can figure out which one it will be. Okay, so you need to figure out, in the final product, will I end up with the cis or the trans double bond? Do I need to flip this one? Yeah. How do you know? Yeah, the hydrogen and the bromine are pointing in the same direction. So I need to flip it. So let's look at it currently. How are my carbon groups pointing? So they look almost like a cis. We'll say cis-like. Okay? So I need to flip it. So when I flip it, it'll make it go from cis-like to trans-like. So you can... It'll end up with something like that. Right? Do y'all agree with that? So just look at it originally. Do I need to flip it? Yes. Then, flip it and it's going to be the opposite way it looks like. If no, then keep it the same. All right? Because the big thing with E2, it doesn't want crowding, remember? Because everything is happening at once. Just like SN2, the driving force for all of this is crowding. So does it look like, because I'm going to be taking off the hydrogen and the bromine. So over here to over here, where are they further apart? At the top or the bottom? The bottom, right? The hydrogen and bromine are further apart. And so because of that, there's less crowding when the base comes in, because we've put the two leaving groups as far apart as possible, okay, the 180 degrees, which makes it less crowded. Okay. Huh?
There's another hydrogen on there that's not going on, or how's that working?
Oh, I'm just showing you the there's other hydrogens on there. I'm just showing you the one that I'm looking at. Mm-hmm. What is what? Oh, your ethyl's going up and this one's going down? That's fine. Just as long as they're opposite. I just chose to flip this side instead of that side. But if you flip this side instead of that side, that's the same exact product. That's fine. The last thing I want to show you for this, and then we'll start our review, or a break and then review. One thing you can do, this occurs with iodines. Now, how many iodines did I just put on there? 2. Now, E2 can also occur like this. So if I put my base in there, what normally will this take off? The base will take off hydrogen. But in this case, what is it going to take off, you yelled out? A halogen, yeah. So hydrogen and halogen are actually very similar in kind of shape and size. So what it will do, it will take off the iodine just like it was a hydrogen. Okay, so let's even pretend it's a hydrogen if you want. So where would those electrons go, that bond? To make a double bond, right? Which will force what to leave? Iodine. Oops, I didn't. Forming that double bond. So the only difference between this one and the other one was, did I take off a hydrogen at the beginning, or did I take off another iodine? How can you tell if you're going to do, two iodines versus a hydrogen and maybe an iodine? How many iodines did I show in that structure? 2. So that's what you're looking for. If you see 2 iodines, you're going to take 2 iodines, you're going to leave, essentially. If you look at the one above it, what do I have circled? Hydrogen and bromine. Do I have 2 halogens there? No. So do I have to do the 2 halogen mechanism? No. So that's what it's the same exact mechanism. Do you see that? Instead of a hydrogen, you have an iodine. But if you want to know when to kind of even think about that, is do you have the 2 halogens or do you just have the 1? Iodine is the one that works the best for this, and that's usually the one you see in this reaction. Let me see if they... They also use bromine. So bromine or iodine will work. But you're going to see 2 halogens on there. Mm-hmm. I would say it would still go. Okay, so don't think of this as another reaction. Just think of, okay, the E2 could look like an H in halogen or 2 halogens. Okay, but the same thing occurs. You see, what did I make at the end? A double bond, right? And how many arrows did I use to get there? The 3 arrows, right? Which is the same 3 arrows you have in the other mechanism. So the mechanisms are the same. Everything's the same, except do you take off that the halogen there or the hydrogen? Okay, so that's it for today. All right, so let's start reviewing a bit. So I wrote down some problems, but before we look at those, let's look at the vocabulary. Okay, what is an enantiomer? Mirror images, are they superimposable? No. Do they have the same or different physical properties? The same. What can they do different? How they rotate light and how they react with what? Other chiral centers. What about a diastereomer? What's that? What? They're different? How? In every way? That's okay. We're going in a direction. So they're not a mirror image, right? So basically, they're not identical and they're not enantiomers. So they're diastereomers. What does a racemic mixture mean? 50-50 of each. You have 50% of your R, 50% of the S. So do those rotate light? No, it can't. They cancel each other out. If I'm looking at a Fisher projection, going right and left, is that wedge or dash? Wedge, and up and down? Dash. What does meso mean? Yeah, internal plane of symmetry. And what do you call a mirror image of a meso compound? Identical. Okay, so work these out. You can work on in groups if you want. So this first one, just tell me, are these R or S? This one, here's the original. I want you to draw an enantiomer of it and a diastereomer. And then down here, I want you to see you see there's two of them. Tell me if those pairs are enantiomers, if they're diastereomers, identical, and then in addition, are they meso? So, can you see all of them now? So work for a few minutes together, and then we'll check them. Okay. So this one's R, this one's S for the people who want to listen to it. So remember, this is probably the harder one here. You're looking one carbon at a time. So directly coming off, we have CH2, CH, CH2, CH2. Is there one with less hydrogens? Yes, the CH. Okay, so that's number one. Then we go to the next carbon, CH2, CH2, CH3. This one has the most hydrogen, so that'll be number 4. Then we go CH2 versus OH. OH is a higher priority than CH2, so that's number 2. So just keep going down the list until one of them either loses or wins. Okay? All right, now let's look at this one. We want to draw the enantiomer. What does that mean? Mirror image. So how do I draw that? Yeah, the top and the bottom will look the same. And then what changes? The OHs, where do I put them? On the left or the right? The left. All of them? Yes. Now going back to the original, how can I, there's several options here for diastereomer, but what do I need to do? Yeah, keep at least one the same and one different. So let's say we want to keep this one the same, the first one. So where do I put the OH? We're keeping it the same to the right. Let's change this one. So then OH would go to the left. And let's change this one too. OH is on the left. Now you could have had a completely different answer, right? You probably do, unless you did the same exact one as me. But there's several options there. As long as one of your stereocenters changed, like down here, and then one stayed the same. It doesn't matter which one you change or which one you stay the same or how many. The only requirement is one has to change, at least one, and at least one has to stay the same. Okay? Any questions on that one? Okay. Now let's look at down here. We had to decide, are these enantiomers, diastereomers are identical? And are any of these meso? No meso. So let's look at this first one. Now, what's on the wedge and the dash here? Cl and bromine. What's on the wedge and the dash here? H and CH3. So you can't just do a shortcut and just look at the wedges and dashes because we didn't just switch chlorine and bromine. So let's look at this and label it as either R or S. So what would be 4? H. Now it's going to be 4 for both of those. And then what would be number 1? Bromine. Then 2. And then 3. Methyl. Okay, so let's look at this one first. Is our number 4 on a dash? No. So what do? Change it. So what does this look like? It looks like a 1, 2, 3. It looks R, so it's S. And then what about this one? 1, 2, 3. What does it look like? Looks R. Do we need to change it? Yes, so it's S. So we have SS. What is that? Did anything change? So what is that? Identical. So that's one way that, like, the sort of foolproof way, sort of, as soon as you could do R and S fine, is just comparing. You see S went to S. Nothing happened, so they're identical. Now, what if the S changed to an R? Then it would have been an enantiomer. A diastereomer, you actually have to have 2 stereocenters. Because remember, the requirement, one has to change, one has to stay the same. So how many do you need? 2, a minimum of 2. So this one, could this possibly be a diastereomer? I'm not saying it is or isn't, but do I have 2 stereocenters? Yes, so now diastereomer really is an option. It wasn't even an option here. So let's look here. My CH3, it's on a wedge here. What is it over here? A wedge. So what did it do? Stayed the same, right? What about over here? It's a wedge, and now it's a dash. So it changed. So what is this? Diastereomer. Then I drew another one here. What is this one? First of all, are these meso? Yes, because you see the plane right here and right here. Okay? Now look at it further and tell me what you see. Identical. Why identical? It looks like mirror images, right? You see the OHs reflect each other. But what is it? They're meso. Normally a mirror image would be what? An anomer. But in this case, when they're both meso, it's identical. Okay, and so those are the type of problems you're going to see for Chapter 5. Okay, so let's look at Chapter 6. Let's go over the vocabulary first. Okay, so kind of the chart of all of them. Which one, SN1, SN2, E1, E2, which ones, or one, has two transition states in their energy diagram? The ones, so which are SN1 and E1. Which one has one energy hump? The twos. Which ones can rearrange? The ones. Why? They form a carbocation. So SN1 and E1 both can rearrange. Which ones in the mechanism, everything happens in one step? SN2 and E2. Which ones are second order? The twos, SN2, E2, and then which ones are first order? SN1 and E1. Which ones prefer a negative base or nucleophile? The twos. And which one prefer neutral? The ones. Okay, so now let's see what we should do first. Okay, so here's some problems. Now up here, I want you to name these, and then also label for each position, is it primary, secondary, tertiary, just where the halogen is, not every position on carbon. And then over here, I want you to tell me if it's going to be SN1, SN2, E1, E2, or a combination, and then tell me what the product will be. So kind of work together and see if you can figure those out. All right, let's take a look at these. How do we name the first one? How many in the longest chain? 5. So that's pentane. It's ane if it's all single bonds. If there's a double bond, it would be ene. Okay, and how do I name F? Fluoro, and then methyl. Which one comes first? Fluoro. And how do I number those? 2 fluoro, 4 methyl. Why not the other way? Huh? Alphabetical. Do you see that right here? They're both 2 away, right? I could have gone 1, 2, 3, 4. So I could have gone 4, 2, or 2, 4. What you do at this point, because not one of them has more branches, right? They both have 1 branch each. So then you just go alphabetically. Fluoro comes first, so we name it 2-fluoro. Okay. No, because single bonds with straight chains do not have cis or trans, or they're always rotating. Only double bonds and rings will have cis and trans. So can this one have cis trans? Yes, because it's a ring. What do we name this one? Before we do that, this right here, is that primary, secondary, or tertiary? Secondary. Because we look at where the fluorine's connected, which is right here. Now, how many bonds to carbon? 2. 1, 2. How do we name this one? Cyclohexane. And what's this? Bromo. And then chloro. How do we number these? 1, 2. And why does bromo get 1 and not chlorine? Not because it's bigger. Alphabetical order. The bigger part, that comes with R and S. Naming is just alphabetical order usually. And what is, trans. And what about this one is, what is primary, secondary, or tertiary? Secondary, because right here it's bonded to 2 other carbons. And then this one, secondary. So I mean all of them secondary. Any question with those? Okay, let's look at these. So let's analyze them. What type of carbon do I have here? Secondary. And what about this? Is this negative or neutral? Negative because of the sodium. So then you look, is that small or bulky? Bulky or large? So what does that add up to? E2. Okay, and an E product, what do I always have in there? Double bond. Where will the double bond go? The left or the right? Left. For chapter 6 sake, it goes to the left. Because we just learned it technically goes to the right. Okay. What about this one? With neutral and tertiary. So what is that? SN1 and E1. What would the SN1 product be? What would be on there? OH, where do I put the OH? Where the bromine is. And E1, a double bond where? I can go, say, up, down, or left. Left. what do I have on this one? Primary, secondary, tertiary? Primary. Negative base is smaller, bulky. Small. So what did you say? SN2. And what will I do with the SN2? OH, where? Where the chlorine is. Any questions on those? Okay, now we need to look at mechanisms. The last topic in 6. And we're going to do all of them. Okay, so do the first one. Look at it and tell me the mechanism. What is a mechanism, first of all? What are we going to do with all the arrows and everything? This first one, is it going to be, SN1, SN2, E1, or E2? SN2, because we have, let's look at this. This is what type of carbon? Primary. And the base, or nucleophile? Negative, right? Small or bulky? Small. So that means SN2. Okay, so we can see the product here. Remember, for mechanism, I always give you the product. So use that to cheat if you want, essentially. You can see what happens. Is there a bromine on there? No, so that's going to have to leave, right? What is on there? OH, so it's going to make a bond. So OH makes a bond where? Where the bromine, where the carbon is, right? I mean, carbon where the bromine is. Right there. And then what leaves? Bromine. Is that it? Yep. So an SN2 mechanism will always look like this. What about the next one? What do we have? How do you know it's elimination? Look at the product of the double bond. So I know it's one of my E's. So then let's look right here. What do I have? A negative. So which one will it be, E1 or E2? E2. Your 2's like the negative. Okay, so this is going to act as a base. So what will it take off? Hydrogen. Where is the hydrogen it'll take off? On a carbon. Which carbon? Is it going to be the carbon where the bromine is? No, because that's going to be your leaving group. Methyl, methyl, or ethyl? Ethyl. You can see right here. Do you see where it's at? So you know it's one of those. So it's right here. So it's going to grab hydrogen. And what does hydrogen do? It leaves this bond to make a double bond. And then what happens? Bromine leaves. So again, that is always your E2 mechanism. A base will grab a hydrogen. Hydrogen will leave its electrons to make a double bond, and your leaving group leaves. That will always occur. Okay, let's look at the one below it. What do I have in my product? A double bond. So I know is it an S or an E? E. Oops. E. And then how do I know it's E1? This is neutral. So for your ones, what's the first thing that always happens? Leaving group leaves. And then what is on your carbon now? What charge? Positive, yeah. So this one's an elimination. So again, what do we form here? A double bond. So what do I need to do? My leaving group's already gone. So what? Grab a hydrogen. Which hydrogen? The one to the left. Because you see the double bonds between those two carbons. So this water is going to come over here, grab the hydrogen, and then what does hydrogen do? Leaves its electrons to make a double bond. Is that form the product? Yes. So basically, it's similar to E2, except it happens one step at a time. First, the leaving group leaves, then you take off your hydrogen. And it always goes in that order. Okay, let's look at the last one on the next page. And this is the last problem. Okay, what will this be? Do I form a double bond in the product? No, so I know it's an S or an E. So I know it's an S. And then what is this? Neutral, so it's which S? 1. Okay, what's always the first step for your ones? Leaving group leaves. And what charge is on my carbon? Positive. Okay, now, or I'll give you a second to write that down. Okay, now look at our product here. Did I make my leaving group leave? Yes. Now, what is on there? What do I need to add? An OH. You could see that in my product, right? Where does that come from? Water. So I'm going to make my oxygen make a bond to that carbon. And what's the charge on that oxygen? Positive. Okay, am I there yet? Does this look like that? We're close though, right? What's the only thing I need to do? Take off a hydrogen. Using what? Bromine. So bromine's going to come over here. Take one of the hydrogens off, because you look, it's OH, it's not OH2. Do you see that? And then hydrogen will leave its electrons on oxygen to make a lone pair. If you want to show it leaves as HBr, but this part right here. And again, this is always the mechanism for SN1. It won't change. Your leaving group leaves, then your nucleophile attacks, and then take off that extra hydrogen. And how do you know which mechanism to do? You just figure it out, just how we did it before. Yeah. You know, you decide, okay, was this SN1, SN2, E1, and as soon as you know, then you know that's the mechanism you use. The biggest thing here, you know, I give you a product, okay? So look at what product you have, And then from there you can tell at least if it's an S or an E, right? What does the E always form? Double bond, and the S substitutes, okay?